everyone, and good morning. My name is Laurel, and I'm very happy to chat with you today about adaptive feature detection for improved measurement of structural orientations using core imagery. Let's get started. High-quality structural measurements play a key role in building effective geological models and in predicting the geotechnical behavior of an ore body. Measurements of fracture, joint, vein, and fault orientations all contribute to the evolving understanding of an ore deposit and are integral to making informed geological and engineering decisions. Recent efforts have focused on developing automated methods to obtain structural measurements from a combination of RGB and laser profiler drill core imagery, examples of which are shown to the right. Obtaining structural measurements in an automated fashion gives rise to some potential benefits over the standard industry practice of collecting structural measurements manually. The first of which is acceleration of the otherwise lengthy and expensive process of taking manual measurements. Additionally, it can help to improve measurement consistency. As well, it also enables us to output larger quantities of high-quality data like never before. Reliable and accurate structural measurements, however, require a robust automated solution, one which is capable of adapting to variations in drill core. Now, in order to reliably detect drill core features from a wide range of deposits using a single automated solution on drill core imagery without manual intervention, the following drill core characteristics must be considered. First of all, size. Features inherently come in different sizes. For example, a vein could be narrow or large, and this affects feature search criteria relative to the drill core size. Surface texture. Varying roughness or regularity of the drill core surface also affects thresholding. Rock competency will impact the ability to automatically detect features, especially those in close proximity. Also, image resolution. We know that improved image resolution will enhance detection of both large and small features, but this can also prompt required changes to be made to existing feature detection workflows. Finally, driller's marks. A wide variety of markings can be used on the drill core. Therefore, color is not always an effective feature discriminator. For example, a black orientation line may appear in a photo to be a fracture. While the majority of the latter case, driller's marks, could be addressed by emphasizing the use of laser profiler imagery, drill core size, texture, competency, and data resolution just can't be controlled and must be tackled using a more adaptive approach. So what might that look like? Take, for example, a fracture detection task. In this case, we can use specific characteristics which define our target feature, the fracture, to adapt the automated process to search specifically for just that. Since fractures are defined as breaks in otherwise competent drill core, our automated process can be primed to search for deviations in the drill core surface. In this case, we have a high-resolution profiler capturing every bit of detail along the drill core, and this can be seen in green in the third image from the left. To further locate the fractures, we can use the fact that fractures can be represented as uphole and downhole facing surfaces along the core. If we target only these surfaces from the texture image, the fractures then become the dominant feature, as shown in the final image on the right. Of course, in this beautiful detail, we can see that a number of other uphole and downhole facing surfaces exist. However, their size distribution is much different than the fracture signal and therefore can be modeled statistically and removed. For this reason, we have developed a statistical method to highlight target features, which is robust against variation in core texture, competency, and resolution. This is an iterative method which starts with an evaluation of texture variance, which is then compared against an acceptance criteria. If the criteria is not met, an image processing filter is applied to further reduce texture variance, and then the process is repeated. Here is a single row of drill core which has some texture and a couple of fractures cutting across the core. With each iteration, a filter is applied to reduce texture variance. The newly filtered image is passed back into the algorithm, and the texture variance is reevaluated and addressed accordingly. Finally, this process is repeated until the acceptance criteria is met. Using this method can overcome variability in drill core characteristics, leading to robust feature detection. Once detected, feature orientations can be calculated directly from laser profiler imagery, and in this way, application of the adaptive feature detection method has the potential to generate improved structural measurements for data-driven geological and engineering decisions. Thank you.